Okay, let's unpack this. You've handed us a stack of fascinating sources all about something absolutely critical to modern applications in today's lightning-fast world of cloud computing, AWS API Gateway.
It really is central, isn't it?
Totally. Our goal for this deep dive is to quickly make you well-informed on this complex but, essential topic, give you those aha
Mm.
moments that cut through the noise.
And there's definitely some noise around it.
For sure. The core problem, as our sources highlight, is that modern applications are constantly being broken down into smaller, independent pieces, what we call microservices.
Right, that architectural shift.
It's brilliant for agility, for scalability, but it creates this monumental challenge. How do you manage all that traffic, making sure it goes to the right place securely, efficiently, without, overwhelming your backend services?
Exactly. And that's where API Gateway steps in.
Yeah.
Indeed, what's fascinating here is how API Gateway isn't just another service, it's really a strategic imperative that directly addresses this architectural shift.
Strategic imperative.
Think of it as the ultimate digital front door for your entire application ecosystem. It provides a unified, intelligent entry point for everything, from external consumers hitting your mobile app to internal microservices communicating seamlessly with each other.
So like a single address for everything.
Pretty much, it effectively functions as a reverse proxy, positioning itself intelligently in front of one or more APIs, thereby decoupling clients from backend services.
Decoupling. That's key.
Yeah.
Absolutely. It means your client applications don't need to know the intricate details of your microservices architecture. They can develop independently, deploy independently, without messing up the client-side logic.
Okay, that makes sense.
And crucially, as the sources emphasize, it handles all that undifferentiated heavy lifting, those essential but non-value-adding tasks like traffic management, caching, authorization, monitoring.
The stuff you have to do, but doesn't directly make your app unique.
Exactly. This frees your back-end teams to focus purely on their core business logic, which is, well, a massive efficiency and innovation gain. Right. So our mission today is to cut through the complexity of your sources and distill the most important nuggets of knowledge about API Gateway.
Get to the heart of it.
Yeah. We'll explore its fundamental architecture, dive into its varied uses by dissecting its three distinct API types: REST, HTTP, and WebSocket, I think,
Kind of them.
and uncover its powerful, multi-layered security fortress. We'll show you not just what it is, but why it matters, and how it can totally transform how you think about building scalable, secure, and even monetizable applications.
Yeah, how it fits into the bigger picture.
Plus, you'll also learn that it's a fully serverless service with a true pay-as-you-go pricing model.
Which is huge. No minimum fees, no upfront commitments.
You only pay for the API calls received and the data transferred out, making it incredibly cost-effective for fluctuating traffic and just a perfect fit for the modern cloud, right?
Absolutely. Very flexible.
So having set the stage for why API Gateway is so critical in modern architectures, let's pull back the curtain. Let's peek inside its architecture, starting with the very core components.
The building blocks.
Exactly. Every API, Gateway API, is essentially a structured collection of three things: resources, methods, and integrations. You can imagine building a house. These are your foundation, your walls, and your connection to the utilities.
Good analogy. Foundational stuff.
Let's begin with resources. These are the logical paths clients access in your API. Think of them as specific, organized addresses on your digital front door.
Like street addresses for your data.
Yeah. For example, you might have a resource like users to manage user data or products to handle product listings. The real magic of resources is how they allow you to design intuitive, human-readable paths. They immediately tell a developer what kind of data they're interacting with, much like an organized file system.
Makes it much easier to understand what's going on.
Totally. And what's even better is that these paths can be hierarchical. You can have child resources like users, user-id. See, that's a path parameter.
So it's dynamic.
Right. This clever design allows a single API endpoint to dynamically serve different pieces of information based on what the client specifically requests, like retrieving details for one particular user ID. It simplifies complex data access with predictable patterns.
Exactly. This hierarchical structure is incredibly powerful for simplifying API design. Instead of creating a unique, often cryptic endpoint for every single data point, you establish a logical tree.
Like a folder structure.
Precisely.
Eh.
This not only makes your API more discoverable and intuitive for developers consuming it, but also inherently leads to cleaner, more maintainable backend code. It's a foundational element that dictates how clients perceive and interact with your entire service.
Okay, resources make sense. Paths, hierarchy, parameters, got it. Next, we have methods.
The verbs.
The verbs. These correspond to the standard HTTP actions that define what a client wants to do with a resource. We're talking about actions like get to retrieve data,
Post to submit new.
to update existing data, delete to remove it, or patch each for like partial update.
Right, the standard RESTful action.
So, for our products resource, a POS products method would allow a client to submit a new product entry, while GT products would retrieve a specific entry for an existing product.
Pretty straightforward.
Yeah, and this standardization is a huge win for developers, isn't it? It makes APIs predictable, universally understandable, and incredibly easy to interact with, regardless of the underlying technology.
Absolutely. The beauty of adhering to these HTTP methods is that you're speaking a universal language of the web. It means developers don't have to learn a new syntax for every API they encounter.
They already know the rules.
They already know that a GT request is idempotent and retrieves information, while a POST creates something new. This common understanding greatly reduces friction and accelerates integration time, which, when you think about it, is a huge factor in the speed of modern development.
Okay, resources are the nouns, methods are the verbs. Now, here's where it gets really interesting. The how API Gateway talks to your actual application logic, integrations.
The connection to the backend.
Exactly. The integration is the crucial link that connects your API Gateway front end to the backend service that actually fulfills the request. Our sources highlight a variety of backend integration types, providing, well, significant architectural flexibility.
Let's break down these backend connections. The most common and arguably the most popular for modern serverless applications is the Lambda integration.
Ah, the dynamic duo.
Yeah, that's a good way to put it. It forms a sort of dynamic duo pattern where API Gateway acts as a direct trigger for a serverless AWS Lambda function, which then executes your application logic.
Super common pattern.
It's a powerhouse for modern, event-driven, and cost-efficient serverless architectures because Lambda scales instantly with demand and you only pay for compute time used.
Right. What else?
Then you have HTTP endpoints. This means your API gateway can act as a proxy for virtually any external web service, whether it's publicly accessible, running on premises, or even hosted on another cloud provider.
So it can talk to almost anything with an HTTP address.
Pretty much. It's incredibly flexible for integrating diverse systems. And finally, there are direct AWS service integrations. This allows you to interact directly with other AWS services like Amazon S3 for storage, Amazon DynamoDB for NoSQL database operations, or Amazon Kinesis for data streaming, all without needing an intermediate Lambda function.
Oh, interesting. So you cut out the middleman sometimes.
Exactly. This can simplify your architecture and reduce latency in many scenarios.
That's quite a spectrum of backend options. But within these integrations, there's another key distinction I saw. Proxy versus non-proxy integrations. Could you elaborate on what those mean for us?
Absolutely. This is important. With a proxy integration, it's conceptually simple. API Gateway acts as a transparent pass-through.
Just sends it straight through.
Yep. It forwards the entire client request headers, query strings, bodied directly to your backend, and then returns the entire backend response to the client without modification. It's quick to set up and ideal when your backend expects requests exactly as clients send them.
Okay, simple. What about non-proxy?
However, non-proxy integrations give you much greater control. Here, you manually configure the data flow. You can transform both the request before it goes to the backend and the response before it goes back to the client.
Ah, so you can fiddle with the message.
Precisely. This means you can do powerful things like inject or remove specific headers, convert a request body from an older format like XML to JSON, or even rewrite the URL path entirely to match a legacy backend's expectations.
Wow, okay. That distinction seems crucial for architects then. While proxy integrations simplify setup and are often preferred for ease of use, non-proxy gives you the power to really shape the data flow, ensuring the request precisely matches the backend's needs.
Exactly.
I recall you mentioning Velocity Template Language, or VTL, in relation to this. What exactly is VTL, and why is it so important here?
Yes, VTL, good catch. VTL, or Velocity Template Language, is essentially a lightweight templating language that lets you dynamically transform data formats on the fly within API Gateway before it ever hits your backend.
On the fly, inside API Gateway itself.
Right there. So imagine a client sending an XML request, but your Lambda function only understands JSON. With VTL, you can write what's called a mapping template within API Gateway to parse that XML and convert it into a JSON object that your Lambda expects.
Okay, so it's like a mini translator built in.
Exactly. This capability is particularly valuable when your backend expects a specific format that differs from what the client sends. Or if you need to enrich the request with additional data, like maybe a user ID derived from an authorization token before it reaches the target service.
Right, adding context.
Yes. It introduces a bit more configuration overhead. You have to learn VTL, but the flexibility it offers in managing complex data contracts, especially when dealing with legacy systems or integrating disparate services, can be invaluable for sophisticated API designs. I've seen it save countless hours of development that would otherwise be spent writing transformation logic in the backend itself.
So a bit more work up front, potentially saving a lot of back-end coding later.
That's the trade-off. Now let's follow an API call's lifecycle, step by step. This isn't just a simple pass-through. API Gateway adds significant value at each stage, offloading critical work from your backend.
Okay, the journey of a request.
It's a complex, multi-stage process that significantly enhances the value of the request as it moves through your system.
Got it. Where does it start?
The journey starts with client request reception. The gateway accepts the HTTP request from the client, meticulously extracting its key components. The HTTP method, like DT or POTAID, all the headers, and the request body.
The initial handshake.
Exactly. Setting the stage for everything that follows. Next is a critical stage, authentication and authorization.
Security right at the start.
This is a crucial security layer where the gateway validates credentials, things like API keys, OAuth tokens, or JSON Web Tokens, JWTs.
So it checks the ID before letting it in.
Precisely. Your backend can then assume the request is already verified, allowing it to focus purely on business logic. This offloads a significant security burden from your backend services, ensuring consistent policy enforcement at the very edge of your application. If a request fails authentication here, it never even touches your precious backend resources.
That makes a lot of sense. So API Gateway acts as a strict bouncer right at the door. If a request doesn't have the right credentials, it's stopped before it can consume any of your back-end compute cycle.
Exactly. That's a huge efficiency gain right there.
Okay, so it's authenticated. What's next?
Following successful authentication, the gateway performs routing and discovery. It determines the correct backend service to handle the request.
Figuring out where to send it.
Right. This involves mapping the incoming request path to the appropriate upstream service based on predefined rules. In a dynamic microservices environment, this can involve sophisticated service discovery mechanisms to locate the correct and potentially ephemeral service instance.
Finding the right microservice, basically.
Yes. Then, for non-proxy integrations, the next step is request transformation. As we discussed, using VTL mapping templates, the gateway can modify the incoming request, injecting headers, converting data formats, or rewriting paths to precisely adhere to the specific requirements of the target service.
The translation step, if needed.
Correct. After that comes traffic management. The gateway applies rate limits and quotas using that clever mechanism called a token bucket algorithm.
Ah, the token bucket again to stop it getting flooded.
Exactly. To protect your backend from being overwhelmed by sudden traffic spikes and to ensure fair usage. This algorithm is like having a bucket that fills with tokens at a steady rate. Each incoming request consumes a token. If the bucket is empty, the request is denied.
Okay.
This allows for short bursts of traffic if there are tokens accumulated in the bucket, but then enforces a consistent long-term rate, preventing API abuse. This can be configured at global, stage level, and even granular usage plan level throttling.
That token bucket algorithm is a brilliant way to smooth out traffic spikes without cutting off legitimate users entirely. So if you've got multiple layers of throttling global, stage, and usage plan, how does API Gateway decide which one to apply? Which one wins?
Good question. The narrowest throttling definition that is exceeded will block a request.
The strictest rule applies.
That's right. So if a global limit is 10,000 requests per second, a stage limit is 1,000, and a specific user's usage plan is 100, the user will be blocked if they exceed 100 requests per second, even if the higher limits aren't hit.
Okay, so the most specific limit takes priority.
Yes, this gives you precise hierarchical control to prevent abuse and ensure service stability, even under heavy load. Once validated, potentially transformed and checked against traffic limits, the request proceeds to back-end integration,
Finally talking to the application.
where it is forwarded to the designated back-end service. Finally, we have response handling. After the backend processes the request and sends a response, the response travels back through API Gateway.
The return journey.
Similar to request transformation, the gateway can perform its own set of transformations on the response. Additionally, and this is important for performance, for high-traffic endpoints, API Gateway can serve responses directly from a cache,
Ah, caching to speed things up.
significantly reducing latency and load on the backend.
So if you think about it, that journey shows us API Gateway isn't just a messenger. It's a bouncer for security, a translator for data formats, a traffic cop preventing overload, and even a librarian serving up cached frequently asked questions for quick responses.
It's a pretty good summary.
It's doing an incredible amount of heavy lifting before your request even gets to your application logic. Are there any scenarios where you wouldn't want it to do all that heavy lifting? Like, is it ever overkill?
That's a perceptive question. While centralizing these functions is generally a huge benefit, there are edge cases. For instance, if you have an extremely simple internal-only API with very predictable traffic, minimal security needs, and where every single millisecond of latency is absolutely critical.
Like high-frequency trading or
Yeah.
something?
Maybe, yeah. In those rare cases, adding API Gateway might introduce some tiny amount of overhead. But honestly, for the vast majority of modern applications, especially those dealing with external clients, microservices, or fluctuating loads, the benefits of offloading these cross-cutting concerns far outweigh the minimal added latency or configuration.
The trade-off is usually worth it.
Almost always. The reduced operational burden on your back-end services and the enhanced security posture are almost always worth it.
Now let's talk about where your digital front door is actually positioned. Think about where your users are geographically. API Gateway offers 3 primary endpoint types, each optimized for different geographic distributions and performance needs.
Location, location, location.
Exactly. This isn't a one-size-fits-all situation. Choosing the right one can significantly impact performance, cost, and security for your users.
Absolutely critical choice.
First, we have edge-optimized API endpoints. This is actually the default for REST APIs, and it's designed for API access to geographically distributed clients.
For a global audience.
Right. What happens here is that the service automatically leverages Amazon CloudFront, which is AWS's global content delivery network.
The CDN.
Yeah. This routes requests to the nearest edge location, dramatically reducing latency for users all over the world by caching content closer to them and accelerating content delivery. For a truly global application, this is probably your go-to.
And this is where it gets really interesting regarding security evolution. Historically, to get full Layer 7 protection with AWS WAF for these edge-optimized endpoints, you might have had to set up your own CloudFront distribution in front of API Gateway.
Oh, so you had to manage 2 things.
Exactly, which added architectural complexity and another layer to manage. But now, and this is a relatively recent improvement, API Gateway natively integrates with AWS WAF for all endpoint types, edge, regional, and private.
Okay, so WAF works directly with all of them now.
Yes. This simplifies security posture significantly. You get that global low latency from edge-optimized and deep security customization with Wave right out of the box. This is a huge aha moment for architects, eliminating previous compromises and streamlining security integration.
That's a fantastic simplification. So before this native integration, architects would have to manually configure CloudFront just to get WAF, which sounds like it adds a lot of overhead. What real-world headaches did that cause?
Well, it was a classic 2-layer problem. You'd have to manage 2 separate configurations, right? CloudFront and API Gateway, and you had to mentally model how they interacted.
Debugging must have been fun.
Yeah, debugging traffic flows could be more complex, definitely. And ensuring consistent security policies across both services required more careful orchestration, more room for error. The native integration really allows you to treat API Gateway as the single, authoritative security perimeter, simplifying operations and reducing the chance of misconfiguration. It's much cleaner.
Okay, edge optimized for global reach, now with easier way. What's next?
Next are regional API endpoints.
Regional, so for users closer by.
Exactly. These are deployed in a specific AWS region, and they're ideal for clients primarily within that particular region or nearby, or if your application logic is constrained to a single region for, say, data residency reasons.
Right.
Unlike edge-optimized endpoints, they don't automatically use CloudFront, but they give you the flexibility to deploy your own custom CDN in front of them if you need very explicit control over that configuration.
So you can use a CDN, but you manage it yourself.
Correct. This is often preferred when your consumers are geographically concentrated, you have specific data residency or compliance requirements that necessitate regional deployment, or you just prefer to manage your CDN separately.
Gotcha. And the third type?
Finally, we have private API endpoints.
Private. Sounds secure.
These are the most secure, designed to be accessible only from within a virtual private cloud, VPC, using something called an interface VPC endpoint.
Only from inside your own private network.
Exactly. This is absolutely crucial for internal or private-facing APIs, ensuring no public internet exposure whatsoever.
So perfect for microservice to microservice communication.
This is your ultimate security boundary for microservices communicating within a private network. It's essential for a robust, internal-only API strategy, where you need to guarantee that your internal services are never exposed to the public internet, perhaps for sensitive data processing or internal business logic.
Makes total sense.
Private endpoints facilitate secure, compliant communication between components within your AWS environment. It's a critical aspect of modern, secure cloud architectures, especially in regulated industries. They truly complete the picture, allowing API Gateway to serve as the intelligent front door for all traffic, public or private.
Okay, so you've chosen your endpoint type, you've built your API, but what about managing its evolution from development to testing to production? That seems important.
Crucial, you don't just build it once.
Right. API Gateway gives you powerful tools for this lifecycle management, ensuring smooth transitions and minimal disruption to your users.
Yeah, managing change safely.
A core concept here is stages. A stage is a logical, named reference to a deployment of your API. Think of it like different environments you use. You may have alpha, beta, dev, test, and prod stages.
Standard practice, really.
Exactly. Each stage can be independently configured to interact with different backend endpoints. For example, your beta stage might point to a testing database and a development Lambda function, while your prod stage points to your live production database and stable Lambda.
Isolating environments.
Right. This enables seamless testing and development workflows, allowing you to iterate quickly and safely without impacting your live users.
It's a bit like having separate branches in a code repository, but for your API deployment. You can test new features in your dev stage, gather feedback in beta, and only then promote to prod, all while ensuring a clean separation of concerns and preventing accidental changes to your live environment.
That isolation seems critical for CI/CD pipelines.
Absolutely. Crucial for continuous integration and continuous delivery pipelines.
Related to stages are deployments. What are those exactly?
A deployment is essentially a point-in-time snapshot of your API's configuration.
Like saving your work at a specific moment.
Kind of, yeah. Whenever you make changes to your API, adding a new resource, modifying an integration, or updating authorization, you need to create a new deployment for those changes to take effect. This acts as a version marker for your API.
Okay, so a deployment freezes a version.
Precisely.
And this brings us to versioning. Deployments enable you to manage multiple versions of the same API to run simultaneously.
Which is super useful.
Yeah. This is fantastic because it ensures that existing applications can still call older API versions even after you've published a new one. This facilitates a smooth transition for your user communities, preventing breaking changes for your existing client base while allowing you to introduce new features. It's a lifesaver for larger ecosystems, right?
Definitely avoids the big bang everyone update now problem.
Total.
And here's where you gain advanced control for continuous delivery with canary release deployments.
Ah, the canary in the coal mine approach.
Exactly. A canary release allows you to test a new API version with a small specified percentage of live traffic. For instance, you could route, say, 5% of your users to the new API version, while 95% continue to use the stable older version.
Testing the waters with real users, but limiting the risk.
Precisely. This is a powerful mechanism for real-world testing of new features or bug fixes with minimal risk to your entire user base. If issues arise, you can quickly roll back, containing the impact.
Have you seen this save the day?
Oh yeah. I once worked on a critical e-commerce platform, and a seemingly minor API change caused a bug that affected checkout, but only in specific browsers. Our canary deployment caught it immediately with just a small fraction of users affected. We redirected traffic back to the stable version within minutes, averting what would have been a very costly, very visible outage.
Wow.
It's a key strategy for robust continuous delivery and deployment pipelines. It builds confidence in your releases. Okay, so we've talked architecture. Now let's get into the different types of APIs you can build with API Gateway. If you need a comprehensive, battle-tested solution with a rich feature set, REST APIs are often your go-to.
The workhorse.
Exactly. They are the full-featured workhorse of API Gateway, built on the familiar REST architecture with stateless HTTP 1.1 communication, and they've been a staple in API design for years. They provide a rich set of features that address a wide array of API management needs, making them incredibly versatile.
When you say full-featured, what are some of those key capabilities that really set REST APIs apart? What are the bells and whistles?
Good question. First, you get fine-grained control. This means granular configuration and permissions for each HTTP method: get, post, put, delete, and so on. This level of detail is essential for complex access patterns and security policies.
More knobs to turn.
Pretty much. They also offer built-in caching, allowing you to customize a cache with keys and time to live (TTL) settings to reduce backend load and improve latency for frequently requested data.
We talked about caching earlier, yeah.
And that can be a nuanced cost optimization strategy in itself, as you're trading the hourly cost of the cache for reduced backend compute. Crucially, for many businesses, REST APIs provide API keys and usage plans.
For managing access and maybe charging for it.
Exactly. These are essential for managing third-party developers, offering robust access control, and defining throttling and quota limits for API consumption and even monetization, effectively turning your API into a product.
Gotcha.
Finally, API Gateway can automatically generate SDK generation for various platforms: Java, Python, JavaScript, etc. This simplifies the developer experience for API consumers and makes integration much smoother by providing ready-to-use client libraries.
Okay, so if you need all the bells and whistles, fine-grained control, caching, managing third parties with keys and plans, maybe SDKs, and you're building a classic enterprise-grade application, REST APIs are often the answer. They're the tried and true feature-packed choice.
That's a good summary.
But I understand this robust feature set comes with some trade-offs, like being generally more expensive and having slightly higher latency compared to the newer HTTP APIs.
That's correct. There are trade-offs.
What's the core insight here for an architect making that decision between REST and HTTP?
That's the strategic imperative, really. The insight here is that while REST APIs offer unparalleled control and a comprehensive management suite, you're essentially paying for a Cadillac when maybe a Honda might suffice for many modern internal microservices.
Cadillac versus Honda.
Okay. The real takeaway is discerning when that Cadillac-level management with its rich features for external developers, complex authorization, built-in caching, is a genuine business imperative, not just a technical preference or habit.
When do you really need the Cadillac?
Right. For public-facing APIs, partner integrations, or where detailed usage tracking for billing is required, the REST API's robust feature set is often indispensable. But for a simple internal API consumed only by other services within your VPC, that extra functionality might be unnecessary overhead, both in terms of cost and latency.
That's a great way to frame it. So if you're building a simpler internal service or you're all about raw speed and cost effectiveness for modern workloads, then the Honda equivalent,
Yeah.
HTTP APIs, enters the picture. These are the newer, leaner, and often meaner option, especially for modern serverless architectures, right?
Absolutely. They were introduced specifically to address the need for a more lightweight, high-performance alternative to REST.
And the benefits are significant.
Hugely. One of their biggest appeals lies in their key benefits. Our sources tell us they offer up to a surprising 71% cost reduction and potentially 60% lower latency compared to REST APIs.
Wow, 71% cheaper. That's massive.
It's a huge difference if cost and raw speed are your top priorities. This makes them incredibly attractive for high-volume, performance-sensitive applications, which are increasingly common in event-driven serverless environments.
Why are they so much faster and cheaper?
The why behind this efficiency is that HTTP APIs have a simpler execution path internally within AWS, less overhead, and they're really optimized for direct integration with services like Lambda. Less feature baggage, basically.
Makes sense. Of course, these benefits come with limitations. They have a more limited feature set, you said.
Correct. For instance, they don't natively support API keys or usage plans in the same comprehensive way as REST APIs.
So less built-in stuff for managing third parties.
Right. If you absolutely need those for third-party developer management or monetization, you'd have to implement them yourself with additional services, maybe Lambda authorizers and DynamoDB, or just stick with a REST API. Their security model is also streamlined, primarily supporting JWT authorizers based on OpenID Connect and Oath 2.0 standards.
Which is pretty standard for modern apps anyway.
Exactly. It's perfect for modern identity providers like Cognito, Auth, or Okta.
But here's what makes HTTP APIs truly stand out from many modern architectures, according to the sources. They're flexible private integrations. This sounds like a real game changer. Can you elaborate?
Yeah, this is a profound differentiator for microservices and, frankly, a huge problem solver for architects building inside a VPC.
How so?
While REST APIs were largely limited to network load balancers, NLBs, for private integrations within your VPC, HTTP APIs can route requests to services behind private application load balancers, ALBs, private NLDs, and even IP-based services registered in AWS Cloud Map.
Whoa, okay, so they can talk directly to ALBs privately. That's new.
Relatively new and super powerful. This means they are not just cheaper, but often a superior, more flexible solution for modern microservices that leverage Layer 7 routing, like path-based routing on an ALB and dynamic service discovery via Cloud Map.
Because ALBs let you do smarter routing based on paths and stuff?
Precisely. This direct integration capability removes the need for additional layers or architectural workarounds that were previously required with REST APIs. It provides a more elegant, native solution for architects already leveraging these advanced networking services like ALBs and Cloud Map.
So it just fits better with modern private networking patterns.
Exactly. For building a truly scalable, decoupled microservices ecosystem within a private network, this flexibility is a massive improvement. It simplifies the architecture and reduces complexity.
So if you're all about that modern, high-performance, cost-optimized microservices architecture with flexible private integrations, HTTP APIs are a huge win. They're built for speed and efficiency, making them a fantastic choice for many new cloud-native projects.
Absolutely. A very strong contender for many use cases today. Now, for something fundamentally different, while REST and HTTP APIs are stateless and synchronous request in, response out WebSocket APIs flip the script entirely.
Okay, different paradigm.
Totally. They enable a stateful, full duplex, persistent connection between client and server.
Stateful, persistent, full duplex. Break that down.
Stateful means the connection itself holds information. It remembers who's connected. Persistent means the connection stays open long-term, unlike a typical HTTP request. And full duplex means both sides, client and server, can send and receive data at any time, independently.
Ah, so it's not just client asks, server answers. The server can just talk whenever.
Exactly. This is a fundamental paradigm shift from the traditional client-initiated polling model, where the client constantly asks, do you have new data?
Yeah.
Anything yet? How about now?
Which is inefficient.
Very. WebSocket enables instantaneous push-based updates. Instead of the client constantly asking, the server can simply push data to the client as soon as it's available.
That's a huge difference. So instead of constantly checking, the server can just push information to the client as it happens. That must open up a whole new world of applications.
Precisely. This capability makes them ideal for real-time, event-driven applications. Things like chat applications, where messages need to appear instantly, definitely. Streaming dashboards that display live data without refreshing, real-time gaming for responsive multiplayer experiences, or even IoT device streaming, where devices need to send and receive data continuously with minimal latency.
Anything needing that live two-way conversation.
Exactly. It's a completely different model that optimizes for low-latency continuous communication. The routing in WebSocket APIs is also distinct. Messages are typically routed to backend services based on their content, allowing for flexible message handling based on the data within the message itself.
So the message itself tells API Gateway where to send it.
Often, yes, based on rules you define. And the pricing model is different as well, based primarily on connection duration time and the number of messages sent and received, rather than the number of API calls like REST TTTP. This reflects the persistent nature of the connection.
Right, because the connection stays open. That's a crucial distinction when considering cost models.
Okay.
Wow. Okay, with all these powerful options, REST, HTTP, WebSocket, it sounds like choosing the right one is a critical architectural decision. You, the listener, need a clear framework to choose the right tool for the job.
Definitely not a one-size-fits-all decision.
It's about balancing features, performance, and cost based on your application's specific requirements, isn't it?
Absolutely. This framework provides a clear path, and it's a decision architects face every day. Your choice isn't arbitrary. It's a strategic decision that optimizes your architecture for what truly matters to your application, be it cost, performance, or real-time functionality.
You mentioned a comparison table earlier.
Right. Think of the feature comparison table we're drawing from. It's like a cheat sheet for architects. It clearly outlines the differences in protocol, primary use case, latency, cost, caching support, authorizers, integrations across all three API types.
Having that clear view avoids mistakes.
Yeah, it's surprising how often projects initially choose a REST API out of habit, maybe because it's older or more familiar, only to realize later that an HTTP API would have saved them substantial costs and offered better performance for their specific use case. Using a framework prevents that.
So let's break that framework down. When should you lean towards an HTTP API?
You choose this when your application requires a simple, stateless API with low latency and low cost being top priorities.
Speed and savings.
Right. It's perfect if your primary backend is a Lambda function or a public HTTP endpoint, and if modern JWT-based authorization is sufficient for your needs. It's not the choice if you need complex features like built-in caching or API keys and comprehensive usage plans in the native way that REST APIs provide them.
Okay. Then when do you opt for a REST API?
This is your choice when your application needs a full-featured API with fine-grained control over its configuration. If your project requires built-in caching, robust throttling, API keys, and usage plans for managing third-party developers, or complex authorization requirements like seamless Amazon Cognito integration, then REST API is the way to go.
The Cadillac for when you need all the features.
Exactly. It offers that comprehensive management suite, ideal for public-facing, monetization-driven APIs or complex enterprise integrations.
And finally, when do you absolutely need a WebSocket API?
This is the clear winner when your application requires real-time, bidirectional communication.
That push capability.
Yes. This means scenarios where the backend needs to push data to connected clients without needing a client-initiated request, like in a chat application, a live data dashboard, or for IoT device control. This is a fundamental difference in communication pattern. If you need that, WebSocket is the tool. Okay, let's talk security, because security is arguably one of the most compelling reasons to use API Gateway in the first place.
It handles a lot of the security burden, right?
Yeah, it does. Its philosophy is to centralize security at the edge, offloading complex logic from your backend and ensuring consistent policy enforcement. This is your first line of defense, a robust, multi-layered perimeter around your valuable services, deciding precisely who gets in and what they can do before any request reaches your backend.
Layered defense. Okay,
Yeah.
what's the first layer?
Let's start with IAM permissions. These are fundamental. They control both who can manage the API, that is, create, update, or deploy it within AWS, and who can invoke it, meaning actually call a deployed API endpoint.
Admin versus user access.
Basically, yes. By creating and attaching granular IAM policies to users or roles, you can define very specific permissions, ensuring the principle of least privilege. For example, you can allow a developer role to deploy to a dev stage, but only allow a read-only access role to view prod deployments.
Standard AWS security stuff applied to APIs.
Correct, but often you need more custom logic.
Right. And for more custom security needs, especially when you have bespoke authentication logic, we have Lambda authorizers. You mentioned these. This is like having a bouncer who knows exactly who's allowed in and for what purpose based on any custom rules you define.
That's a perfect analogy.
How flexible can that custom logic be? Can it do anything?
Incredibly flexible. A Lambda authorizer is a really powerful tool for custom authorization. It's essentially a Lambda function that you provide, which API Gateway invokes automatically to control access to your API methods.
So API Gateway calls your function to check permissions.
Exactly. This function can validate anything from a bearer token, like a JWT or perhaps a SAML assertion, to inspecting other request parameters like headers or query strings, or even performing a database lookup to check user roles or permissions stored elsewhere.
Wow, okay. Very customizable.
Extremely. The authorizer then returns an IAM policy document, either allowing or denying access to the specific API resource being requested. This provides immense flexibility for complex, custom authorization schemes that might integrate with your existing identity systems or unique business rules.
Yeah.
It truly puts the power of custom security into your hands, executing it right at the very edge.
Before it even hits the main logic.
Correct. Then there's Amazon Cognito user pools.
Ah, Cognito for user sign in.
Exactly. This is a managed identity provider service from AWS that greatly simplifies user authentication, especially for mobile and web applications. A Cognito user pool authorizer configured in API Gateway validates access or identity tokens issued by a user pool. It automatically handles the complexities of token verification, signature checking, and expiration.
So it takes care of all that JWT validation complexity for you.
Yes, it offloads the entire user management and authentication token validation process to a managed service. Plus, Cognito can also integrate seamlessly with third-party identity providers like Auth0 or Okta or social logins like Facebook or Google. It's a huge time saver for building secure user authentication flows.
Definitely simplifies things. And for managing third-party developers or even monetizing your APIs, you mentioned API keys and usage plans earlier, primarily for REST APIs, right?
Yes, primarily REST APIs offer the full native support. These keys are a simple but effective mechanism to identify the caller. You generate a key, give it to your consumer, and they include it in their request,
Just a unique string.
basically. And usage plans then allow you to associate these keys with specific throttling limits and quota limits. This is essential for controlling consumption, preventing abuse by any single key holder, and packaging your API into different tiers if you're monetizing.
So the key says who is calling, and the plan says how much they can call.
That's right. It's a surprisingly simple, yet powerful mechanism for attributing API calls to specific consumers. For instance, you could issue an API key to a partner, and that key would then be tied to a usage plan that allows, say, 100 requests per second and maybe 1 million requests per month.
And if they go over?
If they exceed that, API Gateway automatically throttles or blocks their requests based on the plan's configuration. This is critical for preventing runaway costs if your backend scales and ensuring fair usage across all your consumers. It's a core component for anyone looking to build a commercial API product or manage external access reliably.
Okay, so that covers who gets in. But beyond that, API Gateway also protects your backend from how many requests come in and what kind of requests they are. It's like having that highly intelligent traffic controller and a vigilant security guard at your front door, making sure your backend isn't overwhelmed or attacked maliciously.
Exactly. Defense in depth.
Let's talk about throttling again. This mechanism is crucial for protecting your backend services from being overwhelmed by unexpected traffic spikes or deliberate denial of service type attacks.
Absolutely essential for stability.
API Gateway uses that token bucket algorithm we discussed earlier to enforce rate limits, steady state, and burst limits, short peaks. This means it allows for short bursts of traffic before enforcing a consistent request rate, ensuring stability and preventing API abuse.
Smooth things out.
And throttling can be applied at multiple levels, right?
Yep.
You mentioned global stage and usage plan.
Correct. A global account level limit shared across all APIs in a region. A stage level limit for all methods within a specific deployed stage like prod, and even a granular usage plan level limit for individual clients identified by an API key.
And the strictest one wins again.
The narrowest throttling definition that is exceeded will block a request. Yes, this gives you incredibly precise hierarchical control to prevent abuse and ensure service stability even under heavy load. This multi-layered throttling is critical for protecting your downstream services from unexpected traffic patterns.
Okay, that handles volume. What about malicious requests? DDoS protection.
Right. API Gateway acts as a reverse proxy, which inherently provides some protection by obfuscating your backend resources from direct DDoS attacks. Your backend IPs aren't exposed.
Hides the real servers.
Exactly. It also integrates with AWS's Global Edge network infrastructure, which provides a first line of defense against common network level. Layer 3 and 4 attacks think massive floods of packets trying to saturate the network.
Okay, network floods. But what about attacks targeting the application itself, like trying to inject malicious code?
That's where Layer 7 protection comes in. For Layer 7 or application layer, attacks like SQL injection, cross-site scripting, XSS, or other attempts to exploit your actual web application logic, it integrates seamlessly with AWS Web Application Firewall.
WAF again?
Yep. WAF can detect and filter malicious web requests based on a set of managed rule sets, like OWASP Top 10, or custom rules that you define. You can even use rate-based rules within WAF that automatically block an IP address if its request rate exceeds a configurable threshold for a short period.
So WAF can automatically block bad actors based on behavior.
It can, yes, providing dynamic, automated mitigation against certain types of attacks or scrapers.
And remember that architectural aha moment we talked about earlier?
The native WAF integration.
Yeah. The native integration of AWS WAF with all endpoint types, edge, regional, and private, now simplifies this immensely, eliminating previous architectural compromises and providing robust Layer 7 protection out of the box, regardless of your endpoint choice.
It really is a big improvement. I vividly recall a time before this integration when we had a particularly aggressive botnet targeting an API.
Yeah.
If we hadn't been able to quickly deploy WAF rules, it would have overwhelmed the backend systems. But the setup back then, putting CloudFront in front just for WAF, was far more convoluted.
More moving parts.
Exactly.
Yeah.
Now, it's a standard, streamlined process. You just attach a WAF Web ACL directly to your API gateway stage. It makes it much easier to combine global low latency with deep security customization. Okay, so beyond who gets in and how many requests are allowed, it's also about what data gets through and how it's accessed. API Gateway provides crucial features for data integrity and secure communication.
Ensuring the quality and safety of the information flow.
Precisely.
A key feature here seems to be request validation and sanitization. What exactly does that achieve? How does it help?
This is about enforcing strict quality control on incoming data before it hits your integration backend. Request validation ensures incoming requests conform to a predefined JSON schema model.
So you define what the request should look like.
Yes, you define the expected structure, data types, string, number, Boolean, required fields, maybe even regex patterns for strings. API Gateway checks the incoming request against this schema.
And if it doesn't match?
It rejects the request immediately with a 400 bad request error, without ever sending it to your backend. By catching bad inputs early in the request lifecycle, it simplifies debugging by providing clear error messages to clients and significantly enhances security by preventing injection attacks or unexpected processing errors in your backend caused by malformed data. It's a crucial guardrail.
Catches mistakes and malicious stuff early. Got it.
Then we have resource policies and VPC endpoint policies. These are JSON policy documents, similar to IAM policies, but attached directly to the API Gateway API itself or the VPC endpoint used by private APIs.
More policies. How are these different from IAM?
They control access based on network context or AWS account context rather than user role identity. For example, a resource policy could restrict API access only to requests originating from specific source IP address ranges, or only allow calls from specific AWS accounts.
Ah, okay. Network level or account level rules.
Exactly. For private APIs, VPC endpoint policies are particularly important. They restrict traffic flowing from an internal network through the VPC endpoint to specific private APIs. This ensures that your internal services are only accessible from authorized internal sources within your VPC, providing fine-grained network segmentation, vital for security and compliance.
Okay, policies for network control. What about general data security best practices?
Well, the absolute baseline is to enforce secure communication over HTTPS using modern TLS versions TLS 1.2 or higher and strong cipher suites. API Gateway makes this straightforward to configure.
Encrypt everything in transit.
Always. For even higher security, especially in highly regulated environments or for critical service-to-service communication, consider using mutual TLS.
Mutual TLS.
Yeah, with MTLS, not only does the server, API Gateway, present a certificate to the client, but the client also presents a valid certificate to the server for authentication. Both sides have to prove their identity with certificates. This provides a very robust two-way trust, ensuring only authorized clients can even connect.
Okay, extra strong authentication.
And finally, this is a big one that cannot be stressed enough. Never hard-code sensitive data. Any secrets or credentials, think database passwords, API keys for other services you call, sensitive configuration values should always be stored securely in a dedicated service like AWS Secrets Manager or AWS Systems Manager Parameters Store, secure string type.
Don't put passwords in your code or config files.
Please don't. Your application should fetch these secrets dynamically at runtime when needed. I once saw a development team accidentally commit a database password to a public code repository.
Oh, no.
Yeah, it led to a security breach pretty quickly. That single incident underscored why this practice is so critical. Storing secrets centrally and fetching them dynamically greatly reduces the risk of sensitive information being compromised if your code or configuration files are ever accidentally exposed. It's fundamental security hygiene.
Absolutely crucial point. Store secrets securely. Okay, switching gears a bit. For many organizations, APIs aren't just for internal use, they're actual products. They can be a significant revenue stream.
The API economy, right?
Exactly. API Gateway's pay-as-you-go model makes it a natural fit for monetization, and it integrates seamlessly with AWS Marketplace, opening up a huge potential audience for your services.
Yeah, the AWS Marketplace integration provides a really straightforward path to sell your APIs to a vast audience of existing AWS customers.
People already using AWS.
Right. The beauty here is that these customers can subscribe to your APIs directly through the marketplace and, importantly, pay for them on their existing AWS bill. This massively simplifies the procurement and billing process for everyone involved. It's an established channel with millions of potential customers already comfortable with the AWS platform.
Makes it easy for them to buy. What kinds of ways can you charge?
API Gateway supports several monetization models via Marketplace. You can offer SaaS subscriptions, which is a usage-based billing model where consumers are charged based on their actual API usage, calls, data transfer, etc., providing flexibility.
Pay for what you use.
Or, for more predictable revenue, you can opt for SaaS contracts, a classic recurring billing model, maybe monthly or annually, regardless of usage.
Fixed price subscription.
Yes. There's also a SaaS contracts with pay-as-you-go hybrid model, combining a base subscription fee with additional usage charges if a consumer exceeds their allocated quota within the contract.
Best of both worlds, maybe.
Could be. This flexibility allows businesses to tailor their offerings. For a developer tool API, maybe SaaS subscriptions make sense. For a premium data service, a contract could ensure predictable revenue, and a hybrid model offers that balance.
And how do usage plans fit into this?
Usage plans are key. They are the mechanism you use within API Gateway, primarily REST APIs, to package your APIs into different tiers. Think bronze, silver, or gold levels.
Tiered access.
Exactly. Each tier, defined by a usage plan, can offer varying levels of access, which methods they can call, different throttling limits, and different quotas, for example, requests per month. You then associate API keys with these plans. This enables you to create differentiated products and cater to various customer needs and budgets. It transforms a technical service into a true business enabler, allowing you to define, control, and monetize your API ecosystem efficiently, tapping into that burgeoning API economy.
It turns your API into a sellable product with different options. Very cool.
Okay, beyond monetization, performance is paramount. You want your APIs to be fast.
Nobody likes a slow API.
Exactly. The API Gateway offers several tools to ensure your APIs are not just secure and scalable, but also fast and efficient, providing a great experience for your users.
One significant feature we touched on is built-in caching, which is available for REST APIs. How exactly does that help with performance again?
Right. Built-in caching allows API Gateway to store responses from your backend endpoint for a specified time, the TTL, or time to live. When a subsequent identical request for the same resource comes in within that TTL period,
It doesn't bother the backend.
correct. The gateway serves that response directly from its cache, bypassing the backend entirely. This dramatically reduces backend load, fewer Lambda invocations, fewer database queries, and significantly improves latency for frequently requested data, making your API feel incredibly responsive.
Sounds like a no-brainer for busy APIs.
Well, almost.
Yeah.
Architecturally, enabling caching isn't just a technical decision, it's a nuanced cost optimization strategy as well. You're weighing the hourly cost of the cache instance itself against the savings from reduced backend invocations, plus the invaluable benefit of improved user experience from lower latency.
The cache itself costs money.
Yes, you pay per hour for the cache capacity you provision. So it's a fascinating balance to strike between that upfront cache cost and the long-term operational efficiency and user satisfaction gains. It's a classic example of trading a little upfront complexity and cost for potentially significant downstream gains, especially on high-traffic APIs.
Okay, so analyze the traffic patterns before just turning it on everywhere.
Definitely.
That's a brilliant way to optimize both cost and speed. What else helps performance?
Absolutely. Another critical performance enhancer is CDN integration, particularly when using those edge-optimized endpoints we discussed.
Using CloudFront globally.
Right. By leveraging Amazon CloudFront, content is cached at edge locations geographically closer to your users. This not only reduces latency by serving content from the closest point, but also significantly lowers data transfer costs.
How does it lower costs?
Because data transfer from API Gateway to CloudFront is actually free. You only pay for the data transfer from CloudFront out to the internet, which is generally cheaper than direct egress from API Gateway, especially at volume.
Oh, interesting. Free transfer to the CDN.
Yes, this global distribution via CloudFront is key for applications with a worldwide user base, ensuring a consistent high-performance experience no matter where your users are located, and potentially saving you money on data transfer.
Okay, so we've got monetization, we've got performance, but you can't manage what you don't measure, right? Observability seems crucial for maintaining the health and performance of your APIs.
Absolutely essential, especially in complex systems.
And API Gateway gives you a unified view with powerful AWS tools integrating seamlessly to provide comprehensive insights.
It does. It has excellent observability integrations. First, Amazon CloudWatch. API Gateway automatically publishes a variety of metrics to CloudWatch out of the box.
What kind of metrics?
Things like the number of API calls, count, latency, both integration latency and overall latency, and error rates, 4xx client errors and 5xx server errors. You get immediate visibility into these key performance indicators.
So you can see if things are slow or broken.
Exactly. You can set up custom dashboards in CloudWatch to visualize these metrics and configure alarms to be notified instantly via email, Slack, PagerDuty, whatever, of any abnormal behavior. This allows you to react quickly to potential issues, often before they significantly impact users.
Okay, metrics and alarms. What about more detail? Like, why did an error happen?
For more detailed analysis and debugging, there's CloudWatch logs. API Gateway can be configured to log detailed API execution information and access logs directly to CloudWatch logs.
What's in those logs?
Execution logs capture details about the request processing steps within API Gateway, including errors from Lambda authorizers or backend integrations. Access logs provide a record of each request received, including headers, path, source IP, response status, etc. This provides a granular view which is invaluable for efficient troubleshooting and understanding exactly what happened during a specific API call. If a client reports an obscure error, these logs are usually your first port of call.
Digging into the details. Got it.
And to provide an even deeper end-to-end perspective across multiple services, there's AWS X-Ray.
X-ray. Sounds like it sees through things.
Kind of. This service gives you an end-to-end view of the request path. It traces requests and analyzes performance issues and latencies across the entire application stack.
Not just API Gateway.
No, the whole journey, from API Gateway itself all the way through to your backend services like Lambda functions, calls to DynamoDB, other microservices you might call. X-Ray helps you understand the full journey of a request and visually pinpoint bottlenecks.
So you can see where the time is really being spent.
Exactly. Before X-Ray, tracing a request through a complex microservices architecture often felt like trying to find a needle in a haystack, blindfolded, in the dark. X-Ray provides that critical full-stack visibility. It's essential in distributed microservices environments, allowing you to quickly pinpoint bottlenecks, understand the true end-user experience, and rapidly troubleshoot issues that span multiple interconnected services.
Okay, so we've covered a lot of ground. Like any powerful tool, API Gateway comes with a balance of advantages and potential limitations. Understanding these is really key to a successful implementation. Knowing the pros and cons.
Exactly, allowing you to leverage its strengths while mitigating any weaknesses.
So what are the big upsides for our listeners to keep firmly in mind? Why use it?
Okay, on the advantages side, number one, it fundamentally offers improved performance and scalability. The service is designed to scale automatically on demand, capable of handling hundreds of thousands of concurrent calls with no pre-warming needed. Features like caching and CDN integration significantly reduce latency and improve response times.
Handles load, makes things fast.
Right. Secondly, you get vastly enhanced security. It centralizes authentication and authorization at the edge, provides granular access control with IAM, Lambda authorizers, Cognito, API keys, and offers native integrations with AWS WEF for Layer 7 DDS and bot protection. It builds that formidable perimeter.
Central security control point.
Yes. And lastly, it often provides simplified system design. The gateway acts as that single, consistent entry point, effectively decoupling clients from the complexities of your backend services. This dramatically streamlines your overall architecture, making microservices easier to manage, evolve, and secure independently.
Hides the backend complexity. Okay, those are compelling advantages.
They really are.
But what about the other side of the coin? What are some of the limitations or potential downsides people should be aware of? It can't be perfect.
Good question. No tool is perfect. Every powerful tool has its nuances. First, it can introduce additional complexity. Adding a new layer to your architecture naturally brings more components to manage and configure. It requires specific skills for effective management and configuration. The learning curve for things like VTL, for example, can be a hurdle for some teams initially.
Another thing to learn and manage.
Right. Second, if not designed with proper redundancy and fault tolerance in your back-end integrations, it could theoretically become a single point of failure, impacting your entire system if the gateway itself or its core dependencies experience issues, though AWS builds in a lot of resilience by default across multiple availability zones.
Need to design for failure downstream, too.
Always. Third, there's the consideration of vendor lock-in and cost. Being a managed service from a specific cloud provider, AWS in this case, means you're building dependency on that ecosystem. And the cost, while pay-as-you-go, can become significant in very high-traffic scenarios if not carefully monitored and optimized using the strategies we discussed.
Can get expensive at massive scale if you're not careful.
It can. Finally, there are some hard technical limits. For example, there are payload size limits, currently 10 megabyte, for request and response bodies. That sounds large, but it can sometimes be hit with large file uploads or very complex data structures. There's also an integration timeout, currently 29 seconds to the backend to respond,
29 seconds. Okay.
which can be a constraint for certain types of applications, especially long-running synchronous processes. Those should ideally be handled asynchronously anyway, perhaps using step functions or SQS, but it's a hard limit to be aware of for synchronous calls.
Good to know those hard limits exist. Okay, so what does this all mean for your budget? We touched on cost a bit. Managing API gateway costs isn't just about the pay-per-use model. It requires a deliberate, strategic approach to ensure you're getting the most value without overspending.
Absolutely. Cost optimization is key for cloud success. The first and potentially most significant strategy is to choose the right API type.
HTTP versus REST, mainly.
Exactly. As we discussed, the cost difference is substantial. For applications that don't require the full, comprehensive feature set of REST APIs, opting for the lower-cost HTTP API can result in really significant savings, up to 71% cheaper per request, as our sources highlighted. This is often the biggest lever you can pull for cost optimization right at the start.
Don't use the Cadillac if the Honda will do.
Precisely. Second, use caching strategically. For high-traffic REST API endpoints, enabling caching reduces the number of costly backend service invocations, Lambda calls, database queries, etc. While the cache itself has an hourly cost, this is often more than offset by the savings from reduced backend compute, and the improved performance is a bonus.
Do the math on caching.
Definitely. Third, leverage AWS service proxy integrations where appropriate. For direct integrations with other AWS services like DynamoDB or Kinesis, using a service proxy configuration, often involving VTL, can eliminate the need for intermediate Lambda functions entirely.
Cutting out the middle Lambda.
Yes. This directly reduces per-request costs, since you avoid the Lambda invocation cost, and often reduces latency too, despite the initial complexity of potentially configuring VTL. It's a trade-off where some one-time development effort can lead to significant long-term operational savings on high-volume integrations.
VTL complexity versus running cost.
That's the balance. And finally, reduce data transfer costs. By using a content delivery network like Amazon CloudFront, especially with edge-optimized endpoints, to serve content from edge locations, you not only improve latency, but also benefit from reduced data transfer costs. Because remember, data transfer from API Gateway to CloudFront is free.
Use the CDN for cheaper data out.
Especially impactful for geographically distributed applications serving lots of data. These are all architectural decisions that directly impact your bottom line. So pulling this all together for a secure, resilient, and cost-effective production deployment, having a checklist of established best practices is really non-negotiable. This is about building confidence in your API infrastructure and ensuring it can withstand the demands of real-world usage.
Okay, the production readiness checklist. What's at the top of that list? What absolutely must you do?
First, implement a robust authentication and authorization strategy for every single endpoint. Don't leave any endpoint unsecured. Use a multi-layered approach, maybe IAM for basic AWS access, plus Lambda authorizers or Cognito for user application identity to control access right at the edge. The more critical or sensitive the API, the more layers you should consider. Principle of least privilege, always.
Secure every door.
Exactly. Second, enable request validation wherever possible. Define schemas for your incoming requests and have API Gateway enforce them. This is crucial for preventing malicious input, simplifying debugging by failing fast, and reducing the error handling burden on your backend.
Check the inputs rigorously.
Third, configure usage plans with appropriate throttling and quotas, especially for third-party developers or external clients using API keys. This prevents abuse, ensures fair usage across consumers, and protects your backend services from being overwhelmed by unexpected spikes from a single consumer.
Set limits for external callers. Makes sense. And what about protecting against attacks specifically?
Fourth, absolutely attach AWS WAF to your production API stage. This is your primary defense against common web exploits like SQL injection and cross-site scripting, and provides essential Layer 7 DDoS protection. Utilize rate-based rules for automated mitigation against bots and scrapers. I've personally seen save systems from aggressive bot attacks, buying critical time for incident response teams. It's really a must-have.
WEF is non-negotiable for production.
Pretty much. Fifth, secure sensitive information properly. Store all secrets, passwords, API keys, certs in AWS Secrets Manager or parameter store secure string, and never hardcode them directly into your application logic or configuration files. Fetch them at runtime. This is foundational security hygiene.
Secrets management is key.
Sixth, enforce secure communication. Always use HTTPS, disable old insecure TLS versions like 1.0 or 1.1, and configure your API to only accept modern TLS versions 1.2 plus, and strong cipher suites, encrypting all data in transit. Consider MTLS if warranted.
Encrypt everything strongly.
And finally, number 7, leverage observability tools actively. Don't just set them up, use them. Continuously monitor API performance and error rates with CloudWatch metrics and alarms. Log effectively to CloudWatch logs for debugging. And utilize AWS X-Ray for end-to-end tracing to understand performance across your entire application stack. This comprehensive approach, combining security, rate limiting, validation, and observability, is foundational for production readiness and gives you peace of mind.
That's a solid checklist. Seems like covering those bases is essential before going live.
Absolutely essential. Hashtag TechJags outro.
Wow, what a deep dive. We've really unpacked AWS API Gateway today. From its fundamental architecture, breaking down resources, methods, and integrations, to its powerful, multi-layered security fortress, and even how it can help you monetize your services.
Covered a lot of ground.
We did. What stands out to me is that it's clearly not a monolithic one-size-fits-all solution, but a really flexible framework. That ability to choose between REST, HTTP, and WebSocket APIs feels like a fundamental strategic decision, doesn't it? Truly balancing functionality, cost, and performance based on your specific use case.
It absolutely is a strategic choice.
And that layered defense security strategy, centralizing protection at the edge, coupled with continuous evolution like the native WAF integration across all endpoint types, that really shows its power and maturity as a service.
Absolutely. This deep dive has highlighted that API Gateway is a tool requiring careful consideration and a thoughtful architectural approach. Decisions, even seemingly minor ones like enabling caching or opting for VTL-based service proxy integrations, must be based on a granular cost-benefit analysis.
The architect's balancing act.
Exactly. You're constantly weighing that one-time development complexity against long-term operational savings and performance gains. It's a continuous balancing act. For you, the listener, hopefully you now have a comprehensive understanding of the nuances needed to build a resilient, performant, and secure API infrastructure in the modern cloud landscape, capable of handling everything from simple serverless functions to complex real-time applications.
Yeah, hopefully folks feel much more informed now. So what does this all mean for you, our listener, as you think about building or evolving your own applications? Consider this final thought. In a world increasingly driven by APIs, if API Gateway is your digital front door,
The main entrance.
how much thought are you truly putting into its design, its security, and its strategic function, knowing it could be the single most critical point of interaction for your entire application ecosystem? Something to mull over.
Definitely worth considering deeply.
We highly encourage you to explore the official AWS documentation and security best practices for even deeper insights into specific implementations and configurations. There's always more to learn.